Let's take a look at what it means to factor a polynomial. As we shall see, it depends partly on what kind of coefficients we allow for factors of the polynomial. So if we specify what kind of coefficients we allow, we call a polynomial irreducible if it can't be written as a product of two polynomials, each of degree greater than or equal to 1. So, in other words, a polynomial is irreducible if it can't be written as the product of two non-constant polynomials. Now let's take a look at factoring with integer coefficients. Here we have the polynomial 18x to the fourth minus 50, which we can write as the product of an integer and non-constant, irreducible integer coefficient polynomials with positive leading coefficient and no common factor that can be factored out from the coefficients of the polynomial. This factorization is unique except for different possible orders of factors. Now, if we allow only integer coefficients, there are irreducible integer coefficient polynomials of any degree, as high as we'd like. For example, if p is a prime number, we have the polynomial x to the p minus 1 plus x to the p minus 2 plus x to the p minus 3, going down descending powers of x down to x to the 2 plus x to the 1 plus x to the 0, which is 1. And this is an irreducible integer coefficient polynomial called a cyclotomic polynomial. Now let's take a look at factoring with fraction coefficients. Here we have a polynomial similar to the one before, except with fraction coefficients. The lowest common denominator of the fraction coefficients is 45, so we can multiply our polynomial by 45 over 45, which is just a form of 1, so it doesn't affect the value. And rearranging, we get 1 over 45 times the polynomial we had before, a happy coincidence, which had the previous factorization. And rearranging, we get a factorization of the fraction coefficient polynomial, where we have a fraction in lowest terms multiplying a product of non-constant, irreducible, integer coefficient polynomials with positive leading coefficient and no common factor that can be factored out from the coefficients of the polynomial. This factorization is unique except for different possible orders of factors. Now, if a polynomial with integer coefficients is irreducible if we allow integer coefficients only, then it is still irreducible if we allow fraction coefficients. Since, as we saw above, we can express any fraction coefficient polynomial in terms of integer coefficient polynomials, factoring fraction coefficient polynomials is equivalent to factoring integer coefficient polynomials. Cool, eh? But there is another standard factorization for fraction coefficient polynomials. Let's take a look at the factorization we had before. Now, these non-constant integer coefficient polynomial factors have leading coefficients, which we can factor out, and rearranging, we get a new factorization where we have the leading coefficient of the original polynomial multiplying a product of non-constant, irreducible fraction coefficient polynomials with leading coefficient equal to 1. This factorization is unique except for different possible orders of factors. Now let's take a look at factoring with real coefficients. Now we had the previous factorization with rational coefficients. Now if we look at x squared plus 5 over 3, we can see it has no real zeros since it's positive for every value of x. So by the factor theorem, it can't be factored into real coefficient linear polynomials. However, x squared minus 5 over 3 can be factored into linear real coefficient polynomials when we factor it as a difference of squares. So we have a new factorization where we have the leading coefficient of the original polynomial times irreducible real coefficient polynomials with leading coefficient 1, and they are of degree 1 or degree 2. Now this factorization is unique except for different possible orders of factors. Now, since the complex roots of real coefficient polynomials occur in complex conjugate pairs, the fundamental theorem of algebra shows that any irreducible real coefficient polynomial can only have degree 1, degree 2, or degree 0, or in other words, it can only be a linear, quadratic, or constant polynomial. This is different from the irreducible integer or fraction coefficient polynomials, which can have any degree as high as you'd like. So let's take a look at factoring with complex coefficients. So we had the previous factorization. Again, note we have just degree 1 or degree 2 non-constant irreducible polynomial factors. Now, x squared plus 5 over 3 was not factorable with real coefficients, as we mentioned before, since it has no real zeros. However, if we allow complex coefficients, it factors as a difference of squares. X minus square root of 5 over 3i times x plus the square root of 5 over 3i. And we have the factorization that we get from the fundamental theorem of algebra. We have the leading coefficient of the original polynomial multiplying a product of linear polynomials with complex coefficients and leading coefficient 1. Again, this factorization is unique by the fundamental theorem of algebra, except, of course, for possible different orders of factors. Now, this factorization gives all the roots, real or complex, of the polynomial. Now, if you know all the roots of the polynomial, you can write out the complete factorization right away, and vice versa. On the other hand, Galois theory, or the Abel-Ruffini theorem, shows that there is no general way of finding the exact roots of polynomials of degree 5 or greater using basic algebraic operations, or equivalently, there is no general way of factoring polynomials of degree 5 or greater. To summarize, factoring integer coefficient and fraction coefficient polynomials is essentially equivalent. There are irreducible polynomials of any degree. Any irreducible real coefficient polynomial must be constant or linear or quadratic. Any irreducible complex coefficient polynomial must be either constant or linear. There is no general algebraic method for factoring a polynomial of degree 5 and above, although there are general algebraic methods for polynomials up to degree 4. And as you'll recall, we were factoring degree 4 polynomials. So that's a basic look at factoring polynomials.